We've all used one, probably dozens of times. But have you ever really stopped and wondered how that little device actually works? Well, today we're going to pull back the curtain on a piece of technology you almost certainly have in your home right now, the thermometer.
Okay, let's dive right in. You know the feeling, right? You feel sick, your forehead's hot, you're just feeling off. So you reach for a thermometer, and in just a few moments, boom, it spits out a precise number. But how? How does this little stick measure something we can only feel, something totally invisible like temperature?
So, before we can understand the thermometer itself, we've got to take one step back. We need to get to the heart of what it's even measuring in the first place. So let's ask the big question. What is temperature, really? Well, it's not some vague idea of hotness. It all comes down to motion on a microscopic level. See, everything around us is made of tiny molecules, and they are never, ever still. They're constantly vibrating, jiggling, and bouncing around. Temperature is simply our way of measuring the average energy of all that movement. The faster those molecules are zipping around, the hotter it is. Simple as that. And this right here is a crucial distinction. While temperature is the state of the molecules, heat is that energy on the move. And it's a one-way street. It always flows from a warmer thing to a cooler thing. This is the fundamental rule that makes thermometers work. When you put a thermometer in your mouth, your body is warmer. So heat energy flows from you into the thermometer until they reach the exact same temperature. So how did early scientists figure out how to make this invisible energy transfer, well, visible? How could they possibly measure it? The answer lies in a simple yet totally brilliant physical principle. Here's the big secret. When those molecules start moving faster, they naturally push each other farther apart. They need more room to bounce around. So the substance as a whole actually takes up more space. It expands. It doesn't matter if it's a solid, a liquid, or a gas. This predictable expansion is the key that unlocked how we measure temperature. Let's look at a super simple example you could even do at home. If you put a balloon over the top of a bottle, nothing much happens. But then, place that bottle in some cold water. The air molecules inside slow way down. They huddle together, and the balloon just goes limp. Now, move it to hot water. Whoa, those same molecules get a jolt of energy, they expand, and they inflate the balloon. Just like that, you've made thermal expansion visible. So how was this simple principle turned into a useful tool? Well, it became the beating heart of one of the most iconic scientific instruments ever created, the liquid in-glass thermometer. Now, this idea didn't just appear out of nowhere. The ancient Greeks knew about thermal expansion, but it wasn't until the 1600s that Galileo made a proper device to observe it. The real game changer, though, came in 1714 with Daniel Fahrenheit. He not only used mercury, but, and this is the crucial part, he added a fixed, reliable scale. That simple addition turned a scientific curiosity into a practical tool anyone could use. And the design is just genius in its simplicity. You have a little reservoir of liquid in the bulb at the bottom. As that liquid heats up and expands, it is nowhere to go but up an absurdly narrow glass tube. This design cleverly magnifies that tiny amount of expansion, making even a small change in temperature incredibly easy to see. And mercury wasn't chosen by accident. It had this perfect storm of properties that made it the ideal candidate for the job. It reacts to heat super fast, it expands in a perfectly predictable way, it stays liquid across a huge range of temperatures, and, this is a big one, it doesn't cling to the glass, which gives you a crisp, clear reading every single time. And for the clinical thermometers, there was one more clever little trick, a tiny kink or constriction right near the bulb. When you take the thermometer out of your mouth, the mercury column breaks at that exact point, trapping the reading in place. This gives you time to actually see your temperature before it cools down. To reset it, you had to do that classic flick of the wrist to force the mercury back through that narrow gap. But as we know, mercury is toxic. Technology needed a safer, faster way to get the job done. So instead of relying on physical expansion, modern engineers turned to the incredible world of electronics. At the heart of just about every digital thermometer is a tiny, ingenious component called a thermistor. The name is just a mashup of thermal and resistor. It's a special kind of resistor with one job, and one job only, to change its electrical resistance in a very precise way as its temperature changes. So here is how it works in just a few seconds. The thermistor at the tip feels your body heat. That heat immediately changes how electricity flows through it.
Then a tiny microchip, the brains of the operation, measures that exact change in resistance, runs a quick calculation, and converts it into the number you see on the screen. It's an entirely electronic process happening in a flash.
When you put them side by side, the evolution is just crystal clear. We went from a purely physical process, thermal expansion, to a purely electronic one. From a visible liquid to an invisible change in electrical resistance. The result? A measurement that's just as accurate, but dramatically faster and a whole lot safer.
Okay, so let's boil all of this down. If you remember nothing else from our little deep dive today, here are the 5 core truths about how a thermometer actually works. First, remember that temperature isn't a thing. It's just a measurement of the invisible world, the average speed of the molecules that make up everything around us.
Second, the magic trick behind every classic thermometer is thermal expansion. It's the simple, reliable idea that when things get hot, they get just a little bit bigger, in a predictable way. Third, the absolute genius of the glass thermometer is how it funnels that tiny expansion into a very thin tube. It's a simple design that magnifies a small change, making it large enough for our eyes to easily see. Fourth, your modern digital thermometer has moved on from physical expansion to electricity. It uses a thermistor, a smart little sensor whose electrical resistance changes precisely with temperature, allowing a microchip to do all the work. And fifth, and this is maybe the most important part, none of this technology would be useful without a fixed, repeatable scale. Whether it's Celsius or Fahrenheit, it's those agreed-upon markings that turn a physical reaction into a universal measurement we can all understand and trust. And this chart here shows just how far we've come. For critical medical readings, both the classic mercury thermometers and their modern digital replacements achieve incredible accuracy, usually within 1/10 of a degree. We've successfully kept the precision while completely revolutionizing the method. And that leaves us with a final thought. We started with a simple glass tube to measure body heat. Today, we have satellites measuring the temperature of the entire planet from space. The fundamental quest to measure molecular motion just keeps evolving. So what new insights will it unlock for us next?